Brewer, who has been a student, a PhD student in our laboratory for the last 5 years. And it looks like Jay has the record for number of family members. So I want to wish all of you welcome and hope you enjoy this event. Jay, as many of you know, gave up a career in aerospace engineering and computer science to take time out to get a PhD in biochemistry. And when he told me that he was going to do this, I wondered whether it was a good idea or not, because I didn't know him. I knew that this was a hard, tough field to be in, and I didn't know whether he had the correct talents and ideas to be able to succeed in it. But actually, it turns out that he has done much better than I ever would have expected, because of his background and his personality and how he's applied it to issues in biochemistry. So we work on DNA replication, and in the DNA replication field, there are a bunch of important big people in this field that have made contributions, but they're very basic contributions. They've tended to make these contributions and then move on. And our lab has had the reputation of digging deeper and going into more mechanistic detail on issues of DNA replication. But we didn't realize that you could dig even much deeper, down to a third level, where Jay has taken us. He's taken us into details that are very exciting, very informative, and we'd love to be able to study things at this level. So Albert Einstein said, "The devil is in the details." I think Jay has the devil by the tail.
Thanks, Bob. So I especially wanted to thank Bob for, like I said, giving me the opportunity to work in his lab. I did come with a little bit different background than a lot of the students here. And I really appreciated working with Bob. He tended to let me do my research in the style that worked for me, and then he helped me put it together in the end into a nice fluid story. And I especially want to thank Lada, who's in the purple over here, so she'll hide as talking about her. But she sat with me, as Bob talked about, for 5 years, looking through my data, helping me look for alternative explanations to the work that we're doing, and then control for that work. And especially what's important is helping me write in a scientific fashion, so that when we publish the work that we publish was great, had little revisions. So today, as Bob talked about, what I'm going to be describing is the binding and cleavage specificities of two nucleases, DNA2 and FEN1, and how their enzymatic activities are coordinated during replication. So DNA is often considered the blueprint of life, and it's used as a template in creating RNA. Now, RNA is involved in complexes such as a ribosome or telomerase, and more importantly, the RNA is used in creating proteins. And proteins are involved in many things throughout the cell, such as structure, signaling, as well as telling the cell when to divide, when to die, and even replication. So you can imagine that if there's damage that occurs to the DNA, this will translate through to proteins. And now what's interesting is damage to DNA can either cause an increase in function in the proteins, a decrease in function in proteins, or the complete loss of function from the proteins. And you can imagine, therefore, that it's important to keep the fidelity of the DNA, and as this is passed on every single time during replication as cells divide. So when the genetic material, or the information that creates the protein, is damaged, what happens in those cases? So what's known is that when we get even a single gene disorder in which one protein is damaged, we can have disorders such as sickle cell diseases and cystic fibrosis. When you have major reorganization of your DNA, you can have diseases such as Huntington's disease or Down syndrome. And what you probably hear more about in the news these days are when we have multiple proteins that are damaged, along with environmental factors. We get things such as colon cancer, breast and ovarian cancer, and Alzheimer's disease. So we know that the cell has evolved many ways in fixing DNA damage. Well, what is DNA damage caused by? There are many factors that can lead into DNA damage, from extrinsic and intrinsic. So we can have things such as X-ray, UV light, anti-tumor agents, which are actually, their job is to kill the cell, and even errors from replication itself. Now, because most of the times the cells don't see damage, they've evolved multiple pathways in which to repair such damage, such as base excision repair, nucleotide excision repair, double-strand break repair, and mismatch repair. Now, what happens when the cell is highly damaged and the DNA is highly damaged? In these cases, we have a halt of both replication and transcription or creation of the RNA. And in these cases, we generally get apoptosis or cell death. Now, as I just talked about, if we get mutations in the DNA and those are incorporated and passed on during cell division, that's actually what's leading to cell death, premature aging, and even inborn disease, as I just showed on the previous slide. So now, as Bob said, our group is particularly interested in how during replication, the cell has evolved to make sure that it maintains the fidelity and error-free nature of the double-strand DNA. So what actually happens during replication? So if you remember, our DNA is double-stranded. So during every cell division, the DNA has to be replicated. And here's how that happens. The MCM helicase will bind and separate the double-strand DNA. Now on what's termed the leading strand, DNA polymerase epsilon, which actually incorporates the nucleotides, will be in complex with two proteins, proliferating cell nuclear antigen and replication factor C. Now on the leading strand, it can actually synthesize continuously, forming one strand of the double-strand DNA. Now because of the directionality of the polymerase and the anti-parallel nature of DNA, the lagging strand must be synthesized in short discontinuous segments known as Okazaki fragments. Now polymerase alpha will begin synthesizing these segments by initiating with a short 10 nucleotide segment of RNA, followed by 20 nucleotides of DNA. Now, after incorporating this primer, Pol alpha is displaced, in which case DNA polymerase delta, along with pCNA and RFC, will continue synthesis until encountering the next or downstream Okazaki fragment. Now, what's important to remember about the polymerases is that both Pol epsilon and Pol delta have a 3' exonuclease function, which allows it to remove the nucleotide or the DNA that it just incorporated. And what that's thought to do is act as an error correction function in itself. And this is lacking in Pol alpha. And because of this, Pol alpha is thought to incorporate up to 3 orders of magnitude higher errors than either Pol delta or Pol epsilon. So as you imagine, we need to remove the RNA before the double-strand DNA can be completed in these Okazaki fragments. So the way this occurs is DNA polymerase delta, as it encounters the downstream Okazaki fragment, during polymerase synthesis, it will displace the RNA into a flap, or single-stranded RNA. Now, this structure is recognized by FEN1, or flap endonuclease 1, and cleaves, generating a precise SNC that's ligated by DNA ligase 1, and therefore we've completed the double-strand DNA. So when I came into Bob's lab, our group was particularly interested in a really rare genetic disorder known as Bloom syndrome. And in this disease or disorder, both copies of a helicase are damaged and non-functional. Now, why was our group interested in this if so few people actually have the disorder? And here's why. Members with this disorder have a very early onset and predisposition to cancer. And it's actually, most people that have Bloom syndrome get cancer around the age of 25. Now the other interesting thing about Bloom syndrome is there's actually a normal distribution of cancers that occur across different tissue types. And even some individuals with Bloom syndrome have multiple tissue type cancers around the age of 25 as well. So what happens at the cellular level that we want to look at? Now in Bloom syndrome cells where this helicase is non-functional, you get accumulation of stalled replication intermediates. And in healthy cells, it's been shown that Bloom is actually recruited to these stalled replication forks and is likely involved in reactivating the replication. So, as I talked about, Bloom itself is a large 3' to 5' helicase, meaning it binds the single-stranded region on the 3' end and tracks unwinding DNA towards the 5' direction. And it preferentially binds and unwinds what we call fork substrate, with 2 single strands of DNA followed by double-stranded DNA. So how might Bloom be involved in actually